What is up everybody, Dak here, and today I'm going to show scientifically how global warming works. So as mentioned previously in the video, I'm going to be looking at this not from a statistical standpoint, which is what's very typical, just showing, oh look, as year increases, temperature increases. No, I'm actually going to be going into the chemistry and the physics of climate change or global warming and showing how the whole system actually works. I'm not really a fan of how global warming or climate change is typically talked about within the media, as it usually just puts all of the proof of global warming onto statistics instead of showing the actual science of how the thing works. So I'm going to be trusting you and hopefully my ability of teaching skills to go through some of the chemistry and physics of global warming. Alright, so the first part I'm going to be talking about in this video is chemistry. Although chemistry is quite an in-depth subject, I'm going to be disrespecting it by making it look extremely simple. We are going to be looking at three main elements in this video: carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen, as well as nitrogen, are basically 99% of what every living thing is made out of. So these are extremely important. These are also non-metals, which means they form covalent bonds. If you've ever heard the term organic chemistry before, that basically is any bit of chemistry involving this guy right here, carbon. And of course, this video is going to be talking about carbon dioxide, so this guy is very important indeed. These numbers down the bottom here, you'll see on the periodic table. What these are the atomic mass units of each of these elements. One atom of carbon weighs 12.01 atomic mass units, and if you have 6.022 by 10 to the 23 atoms of carbon, you have 12.01 grams of carbon. So this number right here, or Avogadro's number, is the conversion between atomic mass units and grams, and is very important. If you have 12.01 grams of carbon, it's called 1 mole, as opposed to 1 molecule, which would be just, say, a single atom. Not a great example, as carbon's usually joined to other things which would form 1 mole or 1 molecule, but for argument's sake, 12.01 grams of carbon is 1 mole of carbon. Now, as mentioned before, these atoms right here, when they join to each other, they form covalent bonds. Carbon has 4 arms, hydrogen has 1, and oxygen has 2. Now, I'm not going to get in depth because these can vary. That's deeper chemistry. But very basically, carbon has 4 arms, hydrogen has 1, oxygen has 2. Say, for example, you can have hydrogen connecting to 1 oxygen. This right here is water. Or you can have hydrogen connecting to carbon, which connects with 2 arms to oxygen. This right here is formaldehyde. So, yeah, not a nice chemical. And obviously a couple more are carbon dioxide, where each of these have their 2 arms connected to 1 carbon, and one carbon connected to 4 hydrogens, which form methane. Another one is hydrogen peroxide, which looks something like this. And if we want to get fancy, this one right here is ethanol, which is of course the most common form of alcohol we drink. You don't really want to be drinking methanol or butanol or anything like that. So yeah, ethanol, the safest one to drink. And of course we can chop all this right here and put hydrogen. That's methanol. So a hydrocarbon, very simply put, is pretty well anything that has carbon and hydrogen. This right here has 5 carbons, so it is pentane. If it had 6, it would be hectane. If it had 4, it would be butane. 3, propane. You get the idea. So basically how carbon dioxide is formed is mainly these 2 different ways. So a hydrocarbon such as kerosene right here, burned with oxygen, turns into water and CO2. Now it's really hard to tell that it's producing water because it's so hot, it's in the form of water vapor. So it's not like water drips out of the end of a flamethrower. So yeah, it's a bit hard to tell. Now another way is basically just pure carbon reacting with oxygen to form CO2. For example, coal burning. Coal is mainly carbon. There is some hydrogen in there, and there's some other things in there too that get left behind as ash. But mostly when coal is burnt, it becomes CO2 with not much water produced at all. So as mentioned before, each of these have their different number of arms. But what happens when they are by themselves, so not connected to anything? Actually, that's pretty well impossible. Hydrogen, when you've got pure hydrogen gas, it forms a link between itself. So hydrogen gas is always in the form H2. Oxygen does the same thing with itself and becomes O2. Carbon does whatever the heck it wants. Now, carbon unfortunately can't become C2 because if you imagine one of these arms would have to wrap all the way back around in order to connect to the other carbon. So carbon usually forms things like graphite, which is in the tip of this pencil. So solids, not gas. Now this is actually quite an important thing because if you have one single carbon atom, it combines with an oxygen molecule to form CO2, carbon dioxide. Now, if you remember, carbon is 12.01 grams per mole. Oxygen is 16, but it's O2. So you've got 16 times 2. So CO2 weighs 44 grams per mole. Do you see what's just happened? 12 grams of carbon becomes 44 grams of carbon dioxide. It more than triples. For the next example, we're going to look at methane, which is CH4. So when methane burns, combining with 2 oxygen molecules, it becomes CO2 plus 2H2O. So 4 hydrogen atoms here, 4 hydrogen atoms here, 4 oxygen atoms here, so 2 times 2 is 4. And we see 2 oxygen atoms here and the other 2 oxygen atoms here, 1 carbon atom here, 1 carbon atom here. CH4 or methane weighs 16 grams per mole and becomes 44 grams carbon dioxide gas. So once again, it almost triples. So basically what I'm trying to show here is if you have petrol, diesel, something like that, when it burns, say you have 50 litres or 50 kilos of diesel, when it burns, it becomes 150 kilos of carbon dioxide gas. It basically triples. So why is this so substantial? About 79% of the atmosphere is nitrogen, about 20% is oxygen, and about 0.1% of the atmosphere is carbon dioxide. Should also put the 2's there. So what does this mean? If you have 1 cubic meter of air, which is 1,000 litres of air, about 1 litre is carbon dioxide. Now, the next thing I'm going to mention is actually something really interesting, which is if you have 1 mole of gas, as mentioned before, CH4, 12 plus 4 times 1 for the hydrogen, so 16 grams of methane, it occupies 23 litres. Now, if you have 44 grams of carbon dioxide, it also occupies 23 litres. This is a really interesting phenomenon, how 1 mole of a gas always occupies, or pretty well always occupies, around this number right here, 23 litres. It does vary depending on temperature, 24, 22, it's pretty common. But for example, O2 is 32 grams per 23 litres. Then nitrogen gas, N2, is 28 grams per 23 litres. So on average, air is about 1.2 grams per litre. So say for instance we have 16 grams of methane gas here, which is about 23 litres, although you can compress it into a can of methane, for instance, and burn it with 46 litres of oxygen gas, you create 23 litres of CO2. But here's the thing, CO2 is only 0.1% of the atmosphere. So what actually happens is when we create 23 litres of CO2, we create the same amount of carbon dioxide that is in 23,000 litres of air. And that's from 16 grams. So this right here is about 10 grams of rubber. It's about 1 centimetre, 2 centimetres, 5 centimetres, something like that. So 16 grams is not a whole lot more than this eraser right here. And that's the amount of carbon dioxide in 23,000 litres of air. 23,000 litres, that is a big water tank. And it's this. That is all the carbon dioxide in there. It's crazy. Now, what happens if you've got 1 kilogram of coal, which is basically, we'll say 90% by mass carbon. So 900 grams of carbon. So right here we've got 900 grams of carbon divided by 12.01 and then multiplied by 44, as it's basically 44 grams per carbon dioxide, and we see 900 grams or 1 kilo of coal will produce roughly 3.3 kilograms of CO2. 3.3 kilograms of carbon dioxide. Now, by the way, in a coal power plant, you get about 40% of the energy from the coal, which means burning 1 kilo of coal generates about 3 kilowatt hours of electricity, which means you can run a 1500 watt heater for 2 hours off 1 kilogram of coal. Now, where I live in Australia, the average household electricity usage is 33 kilowatt hours per day, which means 11 kilograms of coal has to be burnt in order to provide the necessary electricity for my house, and of course all the occupants within it. So that means we're going to be getting roughly 3.3 times 11 kilograms of carbon dioxide released. So about 36 kilograms of carbon dioxide per day. 36 kilograms of a gas. So 36 kilograms or 36,000 divided by 44 grams per mole times 23 litres per mole, and we have 18,800 litres of CO2. Now, do you remember what I said before? Carbon dioxide is only 0.1% of the atmosphere. So this is as much carbon dioxide as is in 18,800,000 litres of air. 18,800,000 litres of air per day. This is how much carbon dioxide the average household puts out. Not cars, just the houses. 18 million litres per day. Alright, so just to put it into perspective, and honestly, this really sucks to say, my household produces the amount of carbon dioxide as not in this tank here, but 38,000 of these tanks per day. 38,000. I, with these boots that I'm wearing on right now, am 6'2". This is a 500 litre tank. 38,000 a day. So now, what about cars, for example? Say we had a car that could do 10 litres per 100 kilometres. Well, surely it wouldn't release that much carbon per kilometre. So that's only 100 mils of petrol per kilometre, this is about 200 mils. So it's not that much at all, right? So by the way, petrol or gasoline, even though it's a liquid, yeah, that's not confusing, is pretty well made up by octane. Now there is of course the octane rating. This isn't to be confused with the octane rating, but it's usually C8H18. So 8 times 12 is 96 grams for the carbon, and 18 times H is 18 grams. So this total is 114 grams per mole of C8H18. So if we've only got 100 grams and it's 114 grams per mole, we can do 100 divided by 114 and we find, say, 0.88 moles of octane. So 0.88 times 8, which is the number of moles of carbon. So we have roughly 7 moles of carbon. So 7 moles of carbon, of course, reacts with 7 moles of O2 to form 7 moles of CO2. Now remember what I said before, 23 litres per mole. 7 times 23 equals 161 litres of CO2 per kilometre. Now, once again, carbon dioxide is only 0.1% of the atmosphere. So every kilometre you drive in a car that burns 10 litres per 100 kilometres, which isn't too bad, you create the same amount of carbon dioxide as is in 161,000 litres of air. Say you have a 50 litre fuel tank and you fill up once a week. In 2 weeks, you would travel, say, 1,000 kilometres. So in 2 weeks, that's 161 million litres of air. 161 million litres of air's worth of carbon dioxide. Am I starting to get through? That is an insane volume of air. And that's just one person driving in 2 weeks, out of a year, out of several years, out of millions of people. This is one person, say, for example, commuting for 2 weeks. So yeah, basically humans have put a crap ton of carbon dioxide into the atmosphere that was previously buried as carbon and hydrocarbons underground. Where does this carbon dioxide go? Well, some of it, of course, does go back into plant matter, but not a whole lot of it does. Most of it just kind of goes from being in the ground into the atmosphere. Because let's face it, it's not like the amount of jungle is increasing. No, it's decreasing. So of course it's going into the atmosphere and staying there. So now the crazy thing about hydrocarbons and coal is humans haven't mined litres of it. They've not mined cubic meters of it. They have mined cubic kilometers of the stuff. Cubic kilometers. That's 1,000 by 1,000 by 1,000 meters. That is 1 billion cubic meters, which is 1 trillion kilograms. So remember this number back here, 18 million litres. If we have 1 trillion kilograms of coal per cubic kilometre, what do? 18 million, oh my God. So for 1 cubic kilometre, we have 18 million times 1 trillion, which is 18. Yeah, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So 1 cubic metre, so 1 cubic kilometre of coal mined is this many litres of air's worth of carbon dioxide. 1,000 million, billion, trillion, quadrillion, quintillion, 18 quintillion litres of air. Now, if you think mining a cubic kilometre of coal doesn't have much of an effect, that's true. But mining 120 cubic kilometres of coal has a goddamn significant effect. This stuff has a goddamn effect. To be in denial of this is just to plug your ears and go, wow, 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 I'm not listening. Christ, oh, I don't believe in climate change. Christ. So what happens? You stop believing in food, all of a sudden you don't have to eat anymore? Yeah, guess what? The world doesn't revolve around you. This is what really pisses me off with this topic, which is people think their political opinion matters more than this. This is real. 1 cubic kilometre of coal. I couldn't find an exact number, but in the past I've seen that coal alone we have mined 120 cubic kilometres. I couldn't be bothered multiplying this number by 120. Once again, a litre of air, this is a litre of air. It is not too small to see. It is significant. This, God, it's unfathomable. I know it's hard to see this many zeros and really make the link, but dear God, the amount of damage we've done to our environment is just crazy. Alright, so I went and did a bit more research just to double check how much hydrocarbon we use per year, and I found 2 different numbers. One of which was 8.5 gigatons of coal, the other was 7.5 gigatons of oil. So just for the sake of simplicity, I'm going to say that's around 15 gigatons of carbon. So 1 gigaton, by the way, is actually where I was talking before in cubic kilometres. 1 cubic kilometre of water is 1 gigaton of water. So basically, if coal had the same density as water, then the two would be the same. But I'm pretty sure coal's heavier. I've never actually held it in my hand, even though I live right near Australia's biggest coal mines. It doesn't matter the volume. The thing that matters is the mass, because as you know, if things get hot, they expand and shrink, but they always weigh the same. Gigatons, what I should have been talking in, but cubic kilometres kind of makes it easier to picture. So yeah, when I said 120 gigatons of coal, no. It looks like 120 gigatons per decade would be more accurate. And even that, it could be 150 gigatons per decade. for argument's sake, we'll say that we've only been using the current amount of carbon since, say, the 70s, with it fluctuating up and down. So yeah, 15 gigatons times 50 years, that's 750, even more. So 750 times the number on the previous page. And now something else I actually wanted to work out. I've tried looking it up before, but it's hard to find a definite answer, which is just how much air is in the atmosphere. See, the problem is there's different layers of the atmosphere, and the further up you get, the less air there is. So even though it might be the same thickness, there's less air. So yeah. So we've got like the troposphere, which is right down near the surface. Then we've got like the stratosphere, the mesosphere, the exosphere. You know, there's a bunch of different ones. And space officially starts at about 100 k's up. But of course, there's not 100 kilometers of atmosphere if people on top of Mount Everest at less than 10 k's need respirators. So in order to work out how much air is actually, well, on the Earth, it's 1.2 kilograms per cubic meter is the density of air, and 1 bar, which is 1 atmosphere, is about 1 kilogram per centimeter squared of area, which is about that. So there is a kilogram pushing down on that, which means there's a kilogram of air all the way above that up to, yeah, basically space. So 1.2 kilograms. So 1 kilogram of air over 1.2 kilograms per cubic meter equals, I think it's 0.83. Yeah. I'm going to guess 0.83. So anyway, by the time you do the conversion, there's 8.3 kilometers of air thick. If the whole atmosphere is 1 bar, the atmosphere is 8.3 kilometers thick. So now area of a sphere, which we call Earth, area equals 4 pi r squared, which equals 4 times 3.14, yeah, we'll just simplify it to that, times, now the radius of Earth does vary because Earth's actually kind of fat. Centrifugal force actually pulls the equator out. So yeah, the Earth's actually kind of fat like this. But on average, I can't remember the exact number, but it's somewhere around 6,500 kilometers in radius squared. So if we do all this, it's basically 12 times 6,500. So 1,000 squared's a million. So it should be about 36 million, about 40 million. And anyway, here's the number I got on the calculator. But I'm just going to see what my number is. 12 times 4 is 48. So 48, 480 million as opposed to 530. See, it's often not too bad to estimate because this is using rough numbers anyway. They're pretty close, so meh. And of course, that's the area of the Earth. In terms of volume, we need to multiply this by 8.3. And because I'm lazy, I'm not going to do that one, which is roughly 4.4 billion cubic kilometers. So yeah, that's a crap ton. But what do we remember? 1 gigaton of coal is roughly, okay, now it's just double checking, and I think this 18 quintillion litres of air was a bit overzealous. I think it was only 1.8 quintillion litres of air. So yeah, there's an extra zero in there somewhere. I don't know which one's the extra zero, but whatever. But yeah, this 18 million up here should just be 1.8 million. As this was for 11 kilograms of coal, or 10 kilograms of coal, it should just be 1. So yeah, there's the number, 1.72 quintillion, 900 grams of carbon per kilo of coal, by the way. So yeah, this is 1.72 million, so 1.72 million cubic kilometers per gigaton of coal burnt. Yeah, now possibly you might have noticed something. This number here, 1 gigaton, we could have possibly burnt 1,000 of these. This number here, times 1,000, 1.72 billion, that's kind of getting close to all the air we have. So yeah, it's very possible that this number here, we can round this number to 4.5. We can round this number to 1.5 billion. That we've increased the amount of carbon dioxide in the Earth's atmosphere by 30%, which is incredibly substantial. And especially too that a third of this CO2 has been introduced in such a short period of time. Now, of course, the only other times in the past where so much CO2 would have been added would have been from things such as volcanic eruptions, which are correlated with mass extinction events. So, yeah, this is bad. This is really bad. So, as mentioned before, is made up of oxygen, carbon, oxygen. Pretty simple. Now, I'm primarily an audio YouTuber. So, something interesting is oxygen has mass. Duh. Everything's got mass. Oxygen got mass. Also on this side, it's got mass too. The same, pretty well. Carbon here also has mass. Now these bonds right here, they are not infinitely strong. They're not solid. They actually act more like big springs. Or not big springs, really tiny springs. And what happens is when you've got a mass connected to another mass with a spring, you get a resonance. So in a speaker, typically resonance frequency is 1 over the square root of CMS times MMS, which is compliance, which is basically how easy it is to push the cone, times the mass of the cone. So if you've got a really easy to push cone, this number is big. If you've got a really heavy cone, this number is also big. 1 over a big number is a small number. So that's a low resonance frequency. A heavy soft sub has a low resonance frequency. Although if you have a really stiff speaker, such as, well, a tweeter, and a really light speaker, such as a tweeter, you end up with a really high FS. So 1 over a very small number is a very big number. It's basically, yeah, kind of the opposite. So these right here represent compliance and mass. So you've got this part here, which is the mass, and this right here represents the compliance. Now these different bonds here have different spring rates. Basically, they act like different stiffnesses of spring, which means that carbon dioxide has several different resonances. What happens is it will resonate at one frequency a bit, another frequency, and maybe another frequency. So these are the 4 resonance peaks, and they absorb energy at those frequencies. Now, it's not sound that they absorb, it's actually light. So, carbon dioxide absorbs light at several different frequencies. Say we have right here, this is an obvious diagram. This is the sun. When the sun shines light at the earth, what happens is we have a really interesting effect. So here we have a very basic graph. Higher frequency of light is up this end, lower frequency of light down this end. So by the way, blue represents a high frequency light and red a low frequency light. Think infrared is below red and ultraviolet is above violet. So the sun is what's known as a black body radiator, which means it puts out a source of light which looks something like this. So it is brightest at one particular color, and it gets dimmer and dimmer and dimmer as it goes towards low frequency red. Right here, by the way, is the human visible range. So this right here, from 400 nanometers to 700 nanometers, is what humans can actually see. 400 nanometers being kind of the bluest, most violet we can see, and 700 being the reddest. Now you might see that this number here is on the low frequency side, and this number here is on the high frequency side. That's because we actually often talk about light in terms of wavelength. So the higher frequency of the light, so if you can imagine a high frequency here, it has a shorter wavelength than low frequency light, which has a long wavelength. So low frequency light has a big wavelength, and high frequency light has a small wavelength. So, as mentioned before, carbon dioxide has several different frequencies at which it absorbs light. And no, none of it is in the visible range. None of it's around the peak. It is actually right around here at 2000 nanometers. This right here is a significant chunk out of, this here is actually not an extremely significant chunk out of the sun's radiation, but it exists nonetheless. So this is solar radiation absorbed by carbon dioxide nonetheless. Now, of course, up here there's actually a bit taken out by ozone, and down here there's a bit more taken out by H2O, water. Water in the atmosphere is also a greenhouse gas, but we'll get into that later. But the really important thing is actually not that it absorbs energy coming from the sun during the day. It's actually a lot more interesting than that. So here's basically the sun during the day. So you can see it's a pretty rough sketch, but this is actually the energy coming from the Earth at night. Now what happens is the Earth absorbs solar radiation and warms up. Then at night time it basically acts like a very cold sun. It emits infrared radiation back into the sky and back out into space. Carbon dioxide actually absorbs a big chunk right at this peak. So it's not necessarily that carbon dioxide is trapping more of the sun's heat that comes to Earth. Is actually that carbon dioxide doesn't let this heat escape at night so easily. So this is where carbon dioxide does its damage. And because the Earth is exposed to the sun, it warms up, then it becomes nighttime, and it goes to rebroadcast its heat. Now, I should also mention it does technically broadcast out towards the sun during the day, even more than at night. So this does actually take effect at night as well. But the main thing is the Earth can't get rid of this heat. So what happens is the Earth gets warmed up a bit, and then it cools down a bit, cool down a bit, warm up, cool down a bit, warm up, cool down a bit. And over time, the Earth gets warmer. This is how global warming works. Basically, the Earth can't emit heat back into space. Remember, the first law of thermodynamics is energy can't be created or destroyed, only transformed. So what happens is all the energy received from the sun either eventually makes its way back into space or just heats up the Earth more and more. So all of this carbon dioxide that we have put into the atmosphere absorbs a crap ton of energy and doesn't let it escape. So the Earth heats up more and more over time. Now, eventually it will get to a point where it goes back into being stable, and the amount absorbed during the day is the amount emitted at night, and it will be flat. But the problem is that temperature is greater than right now. Okay, well, so what? The Earth's a bit warmer. That doesn't really change anything, right? Yeah, unfortunately, it does change things. Of course it does. So, as I mentioned before, this right here, water is also a greenhouse gas. Now, if you've ever heard of humidity, you know that basically when air gets hot, you can more easily evaporate water. For example, blow drying your hair. When you expose water to hot air, the hot air acts drier and can absorb the moisture more easily. And it's the exact same thing with hotter air due to, well, yeah, global warming. Hotter air absorbs more water from, say, the oceans or lakes. And now you may think, oh, that's good. That means that if air can hold more water, it can rain more. But no, it doesn't work like that, because of course it couldn't just work like that. It has to spite humanity by working the least favourable way. So this air holding all this water, so much more water, and you can possibly hear it right now, this rain. I'm currently experiencing the second major flooding event this year. The first time I'd ever seen water levels reach this level was when I was 9 years old in 2007. Since then, I'd never seen water get to the level it has until 3 months ago, when it got to basically the same level as it did in 2007. In 3 months since then, it is flooded again to that same level. Now, just to be clear, these type of flooding events happened twice in my life before 2 years ago. Since 2 years ago, they've happened 4 times. This is because hotter air stores more water. When hot, humid air is suddenly cooled down, it releases all of its water. The more water the air was holding in the first place, the more it dumps. So warmer air, due to global warming, has the effect of creating more significant flooding events. And of course, because it can hold more moisture, it can be reluctant to give it up, which is why it causes droughts. It absorbs water from lakes, streams, crops, and doesn't let go of it until it cools down. And when it is cooled down, it's a deluge. So it erodes the soil, which has now had all the vegetation die in it. These are the effects from global warming and climate change. Another significant effect is on the Earth we have jet streams that typically look like this, but as the temperature heats up, they become more like this. Now, I'm actually going to put an asterisk here because I am not a climate scientist and I know bugger all about jet streams. This is just from memory. But basically, it's kind of like convection, where you've got cold here, and hot at the equator. So these jet streams, they cause more significant and widespread flooding events than typical, droughts than typical. Basically, the tropics move further south and further north, expanding over time, so exposing regions which would usually be in the temperate zone to tropical weather, so farmers can no longer farm the things they typically would, which is really bad. And of course, bigger storms, due to, as I mentioned, more moisture being in the atmosphere, is compounded by sea level rise. The warmer it is, the more ice melts in Antarctica, which increases the sea level. Most of humanity lives at or within 50 kilometers of the sea. So there is an incredible number of people at risk of having their communities destroyed by storms and sea level rise. And of course, one of the dangerous effects is this part here, absorbed by water, because water is a greenhouse gas. The more water in the atmosphere, the bigger this dip gets, the more solar radiation we absorb, which causes us to heat up even more, which causes more water to evaporate, which causes us to heat up more. So this right here, other than the bushfires from droughts, this right here, all this extra water being in the atmosphere, just causes a feedback loop. And this feedback loop is why it's extremely critical for us to get on top of climate change and global warming sooner rather than later. Because we can see a point where the deeper we get into global warming, the harder it is going to be to escape it. So even more water, even hotter, even more water. This is one of many significant dangers. So in conclusion, basically the way global warming works is humans have released a crap ton of carbon dioxide into the atmosphere. Carbon dioxide doesn't let the Earth release its heat energy that it captures from the sun, and it gradually warms up over time as a result. So yeah, I know that this was a bit different from the regular videos I do. I'm probably going to do more scientific videos like this in the future, so if you made it this far, you can get keen for those. And of course, this video doesn't go, well, what's an alternative to carbon-based fuels? Which, of course, there are alternatives, including carbon-based fuels, but just not digging them up from the ground and adding them to the atmosphere, taking the carbon from the atmosphere to turn into fuel. So yeah, just a reminder, if you enjoyed this video, leave a like, leave a comment too, especially too if you reckon I made any errors. I'm pretty damn sure I didn't make any big mistakes. So chances are if you think something's wrong, you're wrong. So anyway, I don't know, have a good day. See ya. Priming. Ah! Jesus Christ. Holy crap. Yeah, alright, that's enough. Oh my god. Holy crap. Okay, a bit more. That's too much fun. Jesus Christ. Perfect. Bloody perfect. Oh my god.